In this video, we're going to go over section R.4 of our textbook, which goes over rational functions, and we'll start with this definition here, and this DEF is just short for definition. So the domain of a rational expression is going to be the set of real numbers for which the expression is defined. In other words, the domain is going to consist of all real numbers except those that make the denominator 0, and this just stands for in other words. And we know this is the case because we know that we can't divide by 0. All right, so we're going to go straight into this example here. We want to find the domain of this guy here of x plus 3 over x minus 1. And we know from the above definition that the domain is going to consist of all real numbers except those that make the denominator 0. So we want to find for which values the denominator, or x minus 1, will be equal to 0. So this is pretty simple. All we have to do is solve for x, and we can do that by adding 1 on both sides. And so we end up with x is equal to 1. So this will tell us that our domain is going to be the set of all real numbers except x is equal to 1. Because if we were to plug x is equal to 1 into our rational expression here, we would get 0 in the denominator. And then we can write this in set builder notation. So we have our bracket here, and we'll say x such that x is not equal to 1. So in set builder notation, this just means all real numbers except 1. All right. So let's look at this next example here. We have a little more complicated rational expression here, and we still want to find the domain. So what we're going to do first is we're going to factor this guy to see if we can simplify it at all and see if it'll be a little bit easier to work with. So if we were to first factor, let's look at the numerator. We have x squared plus 7x plus 10. So we need two numbers that will multiply to 10 and add to 7. And we have, we're just adding these guys here. So it'll be pretty simple. We have x's here, and two numbers that add to 7 and multiply to 10 are 2 and 5. And like I said, we're just adding everything, so we don't need to be careful with the signs there. And then in our denominator, I see that both terms here have a factor of 4x. So I will pull that out. All right, and then we want to find which values will make our denominator equal to 0. So when will equal to 0. Now this will happen for two instances. The first is if x were equal to 0, right? Immediately if we were to plug 0 into here, this entire thing would be equal to 0. And then the other instance is if we were to look at just this term here. So if x plus 5 were equal to 0, we know that this happens if x is equal to negative 5 by subtracting 5 on both sides. So this tells us that our domain is going to be all real numbers, so all x's, such that x is not equal to 0 or negative 5. All right, so now we're going to look at some arithmetic operations of our rational expressions. And the first one is going to be this example here where we want to multiply these two rational expressions. Now in dealing with these guys, the first thing to always do is factor. So In this first expression here, I see a 5 in both of these terms in the numerator, so I'll pull that out. So we're left with x plus 1, 5 times x plus 1 in the top. And then we have this x minus 2 here that we can't simplify further. Now looking at this expression here, we want to factor the numerator. So we have x squared, so we're going to have this here. And then we want two numbers that when we multiply them, they are equal to positive 4, and then when we add them together, they equal to negative 4. So that's clearly going to be 2 and 2. And then we know that if we multiply two negative numbers, we get a positive number. And if we were to add negative 2 plus negative 2, we get negative 4. So that's what we get on top. And then on bottom, notice that we have this guy here, which is going to be a difference of squares, because we have x squared here minus 1, and then 1 is 1 squared. And so using that formula for the difference of squares, we have x plus 1 and x minus 1 in the bottom here. All right, and then we have a few things that can cancel, since when we're multiplying these expressions, we're multiplying everything straight across. So a few things will cancel. We have x plus 1 here and x plus 1 there, and then we have x minus 2 here and x minus 2 here. So multiplying everything across, we have 5 times this x minus 2 on the top. And then on the bottom, we just have this x minus 1 here. And this is our final answer, our fully simplified version that we get when multiplying these two rational expressions. All right, another operation we're going to look at is division here. And the main thing to note when dealing with division is that it's the same thing as multiplying by the reciprocal. So what we can do is just rewrite this. Our first expression will stay the same here. And what we're going to do is multiply by the reciprocal. So if you remember, taking the reciprocal of this fraction is the same thing as just flipping it. So we have 2 on the top, and then 3y plus 9 goes on the bottom. All right. Then if you notice, we can take out a 2 from both of these guys. So we're just left with 1 here and then 3 there. And so we have 2. Oh. There we go. We got 2y plus 6 over 3 times 1 over 3y plus 9. All right, now if we look at both of these terms, we have a 2 in our 2y and our 6 terms here, and then we also have a 3 in our 3y plus 9 term here. So I'll take out a 2 from this guy, and then take out a 3 from this guy. And then we get y plus 3's cancel. And we're left with multiplying straight across, so we just get 2 over 3 times 3 is 9. So we get 2 over 9. All right. Now our next example, we are adding these two rational expressions. And what we want to do in this instant is find a least common denominator, which stands for LCD. And we can do that by multiplying our denominators to get one common one. So multiplying this guy by this guy, and multiplying this guy by that guy. And we have to remember that whatever we do to the denominator, we have to do to the numerator as well to keep this same fraction value, to keep this same ratio. So what we'll do is we'll multiply this guy here by our denominator on this side, on the top and bottom. And then we'll multiply this guy here with this denominator on our top and bottom. All right. So multiplying this out, we're going to distribute this 3x to x and 3 here. So we end up with 3x squared plus 9x. And then in the bottom, we have our x plus 3 times x minus 1, which is now our new common denominator. And then same for this side, we're going to distribute this 2 over, so we get 2x minus 2 times 1, which is 2. And then we have our common denominator on the bottom. All right, now that everything has the same denominator, we can just add straight across. So we have 3x squared plus 9x plus 2x minus 2 all over our common denominator. And then simplifying a little bit further, the only like terms that we can combine is this 9x and this 2x. So we get 3x squared plus 11x minus 2 all over x plus 3 times x minus 1. So that's how you would add rational expressions. We just first want to make sure that we have the least common denominator and then go from there. And we can't factor this. This is the most simplified form, and that's fine to leave our answer like this. All right, so the last example we're going to look at is complex fractions. So this is essentially the quotient of two rational functions, or a fraction within another fraction. Now, looking at this example, what we could do is we could get a least common denominator for these two. But I prefer to work with I guess we would have to get a least common denominator for this guy, and this guy. But I prefer to work with the numerator and denominator separately. So what I mean is I'm going to look at just this guy, subtract these two, simplify as much as possible, and then divide by this one. So we'll start with doing just that. So what we want to do to subtract these two is to get a least common denominator. And since this one, we're just dividing by 1 here, and we have this denominator here, so all we have to do is multiply this guy by x squared plus 4 on the top and bottom. So we get x times x squared plus 4 divided by x squared plus 4 minus 1 over x squared plus 4. And then now that we have a common denominator, we can subtract these guys. We have an x cubed here and a 4x there. So we have x cubed plus 4x. And then we have a minus 1 here, all over our common denominator of x squared plus 4. All right, so this is what we get in our numerator. So this guy and this guy are equal, and then we're dividing by this rational expression here. So let's rewrite our example as the following. So this is our new problem. All I did was take this guy and rewrite it like this, which we found these two are equal by getting a least common denominator. So now we're dividing these two rational expressions. And remember, that's the same as multiplying by the reciprocal, right? So we take our original rational expression here, or the one on the top, and instead of dividing by this guy, we're going to multiply by its reciprocal. So if we had 1 over x plus 2, then the reciprocal is flipping that, so we get x plus 2 over 1. All right. Now, what I'm going to do now is factor this. We can't factor the numerator, but we know that x squared plus 4 is going to be x plus 2 times x plus 2. We have a sum of squares here. And then we know that we have an x plus 2 over here. So these guys will cancel. And then we're left with x cubed plus 4x minus 1 on the top, and then x plus 2 on the bottom. And that is our final answer. Alright, so that is it for this video.